Hola everyone. So lesson 3 of our transformation unit, we're going to talk about stretches. Now, just like when we talked about reflections yesterday, there are essentially two main lines I'm going to stretch from. Okay, I could actually stretch from any line I want, but that's beyond the scope of this course. Either we're going to stretch on the y-axis, so we're going to let our y-axis be the line of stretch, which is the same sort of concept as the mirror line. Okay, so I could go like that, or I could go like that. This would be called an expansion, and this would be called a compression. Okay, but then this line here remains stationary. Okay, what I want you to see though, the visual I need you to understand is when I stretch against that vertical line, this is going to end up being a horizontal stretch. Okay, just like with reflections yesterday. So you're going to find statements like, oh, I have a horizontal stretch about the y-axis. Okay, same thing with the x-axis. If I was to use this as my line of stretch, I'm going to go like that, or I'm going to go like that. Okay, this would be the expansion, this would be the compression. But when I do that, that is a vertical stretch that's happening. So you're going to see statements that say a vertical stretch about the x-axis. Okay, so now what exactly are we doing? This is not in your book, it's just for us to kind of intro with. Stretches are a transformation in which the distance of each x-coordinate or y-coordinate from the line of reflection or the line of stretch, you can use those phrases interchangeably, is multiplied by some scale factor. For example, if the point 2, 3 was to undergo a horizontal stretch, well, let's just take a look at this. The point 2, 3, maybe that's about there, okay? And I'm going to do a horizontal stretch, which means I'm going to change the horizontal distance that point is from the y-axis, okay? So right now, that point is 2 units away from the y-axis, away from our line of stretch or our mirror line. Okay, so let's say I want to do a horizontal stretch of 5. What happens is that distance needs to get multiplied by 5. So now instead of 2 away, it needs to be 10 away. Okay, and so where does that point end up? Well, the point 2, 3 has to end up at the point 10, 3. Okay, now mathematically, I'm hoping what you see right away there is we end up just multiplying the x by whatever the scale factor is. Okay, the y's aren't changing because I'm doing a horizontal item. When I do a horizontal item, it will not affect vertical parameters. Okay, so the new point would be 10, 3. Okay, so now what we want to do is we want to go through a little investigation. And you're going to want your graphing calculator out, and you're going to want to use your table of values, okay? So I'll walk you through that in a sec. Just let's read the question first. Using your graphing calculator, compare the graphs of y equals x squared and y equals 3 f of x. What is happening to the y-coordinate? What would the mapping rule be, and where would the invariant points be? So what I want you to do is I want you to put x squared into your y1, and then 3 times f of x. Well, remember, f of x is x squared. So 3 times f of x would be 3x squared. So that's what's going to go into your y2. Okay, now what I want you to do, this is what the picture should look like. Okay, so the blue graph is the original, and the red graph is the new guy. So the blue graph is x squared, and then the red graph is 3x squared. Okay, now often what happened is in 20-1 we would use the phrase "it looks like it's got skinnier." Essentially though, what we've done is we've gone like this to it. Okay, and by going like this, it takes the growth and makes the growth quicker, and that's why we get this skinnier looking picture. Okay, but what we want to do is we want to compare the y values to see what's exactly happening. Remember that if we're doing a vertical item, we are not affecting horizontal parameters. So I want us to look at our table of values, and I want to compare the y values when the x values stay the same. That's going to tell us what's happening to the y values. Okay, now if you are a Casio, to get into your table of values, you go menu and table. Okay, and then the other thing I want you guys to do right away is change the setting. So menu and table, and then you will see that F5 says set. And then in there you have a start and an end. Can you make your start like 0 and your end like 20 for now? Okay, and then you can still go in steps of 1. If you're a TI, you will get your table feature by going second function graph. You'll notice that it says table as the second function of graph. Okay, so go ahead and grab your tables, and you should be looking at something like this. Now, again, I want to compare when the x values stay the same. So this guy's really easy to read because it's set up with x values the same. Okay, so when x is 1, my y value goes from 1 to 3. When x is 2, my y value goes from 4 to 12. When x is 3, my y value goes from 9 to 27. So what's happening to the y values? They're being multiplied by 3. Okay, so they're being multiplied by 3, and we would call this a vertical stretch by a factor of 3. Okay, so the y values are getting multiplied by 3. The image point or the mapping rule would be x comma y maps to x comma 3y. The invariant points actually would end up on, just like with reflections, they end up on our line of stretch or our mirror line. Remember, those things can be interchanged. So the invariant points would be located on the line y equals 0, which is the x-axis. And the reason they're on the line y equals 0 is because you're multiplying y values here. Well, on the line y equals 0, y equals 0, and 0 multiplied by anything is still going to be 0. Okay? All right. So now we're going to switch it up. This one's a little bit harder of a conversation for a sec. We're going to change the parameter that involves, or like we're going to change the x now, not the y. Okay, so obviously this means we're going to be looking at a horizontal stretch instead of a vertical stretch. Okay, so we're going to compare the graphs of y equals x squared with y equals f of 1/2 x. Now, that means replace x with 1/2 x. Well, what's the difference between what we just did in the previous one? You have to remember that x is right here. So if I replace x with 1/2 x, I'm actually going to get y equals 1/2 x all squared. And then that square will apply to both items. So when I go to clean that up before I put it in my graphing calculator, it's actually going to end up being 1/4 x squared, because the 1/2 gets squared and the x gets squared. That's the big difference here in the numbers between when I'm dealing with a horizontal stretch and when I'm dealing with a vertical stretch. Okay, so what you get is something that looks like this. Okay, again, the blue graph is my original and the red graph is my new guys. Now, it looks like we have flattened it somehow, okay? But when I say the word flatten, I'm thinking of that from a vertical standpoint. That would be something I do vertically. Here I want to look at, what am I doing horizontally? So if I was trying to do something horizontally and move from the blue graph to the red graph, visually, the first thing I want you to see is, hey, I had to have gone like that. Okay, I had to have gone like that. Now, I want to get the numbers to actually prove that a bit for you, okay? So we're gonna go back to your table. So if you're Casio, you can press menu table. And if you're TI, you press second function graph. And I put a few more here because this one's just a little trickier to deal with. If I want to see what's happening to x, I have to look for spots where the y is not changing. Okay, in the last example, it was much easier to deal with because your tables are set up that x doesn't change. It gives you the two y values for the same x value, which is great. But now I want to look at what's happening only horizontally. So I have to find y values that are the same. So I'm going to first pick on 4 because I see that right away. So let me see if I can help you out with a visual here. And I'm going to say, okay, when y is 4, x moved from 2 to 4. Okay, so I'm picking on when y was 4. And originally, my x value was 2, but in the new graph, my x value moved to 4. Do you see what I'm saying? Okay, now let's pick another one. how about we pick on 9? So when y is 9, my x value moved from 3 to 6. Okay, we're going to do another one. I want to take my time with this because I want you to see it. When, let's pick on 16. So 16's here and 16's here. So when y stays as 16, my x values moved from 4 to 8. Okay, so what I need you to see there is this is a horizontal stretch of 2. I'm multiplying all my x values by 2. Now, the horizontal stretch is slightly more confusing because you don't readily see a 2 here. You saw 1/2, not a 2. Well, how would I go from 1/2 to 2? I would just flip it, okay? So the big take-home message here for the horizontal stretch, when you're looking at a transformation equation, the horizontal stretch is always the reciprocal of the parameter that you see beside x. We're going to call that the b value in a second, but the parameter that you see beside x, the reciprocal of that tells you what your horizontal stretch is, okay? For your vertical stretch, I didn't have to think about that at all. Whatever number I saw in front there, that was my vertical stretch. But for the horizontal stretch, there's a little bit more interpretation involved. The horizontal stretch will always be the reciprocal of whatever that parameter is, okay? So the x values are getting multiplied by 2. I'm just going to answer these questions very quick. And then my mapping rule would be x comma y maps to 2x comma y, because I'm taking all my x values and multiplying by 2. Remember that the image points are exactly, this is exactly what I'm doing. There's never interpretation involved in mapping rules. And then the invariant points would lie on the line x equals 0 or the y-axis, because at that point, if x is 0 and I'm multiplying all my x values, 0 times anything is still 0. Okay. So we'll fill in these blanks. Vertical stretches are represented by this a parameter. So we have an a in front of f of x, where a is the vertical stretch factor. We multiply all the y values by a to obtain the coordinates of the transformed points, and invariant points would occur on y equals 0. For horizontal stretches, they're represented by the form y equals f of bx. So we have a b parameter here, but we have to interpret what b is. So here it's the reciprocal of b, which is the horizontal stretch factor. So we multiply all the x values by 1 over b to obtain the coordinates of the transformed points. And then invariant points would occur on the line x equals 0. If you would prefer, instead of saying the line x equals 0, to say the y-axis, that's fine too, it doesn't matter. Okay, so describe the transformation of y equals f of x and state where the invariant points would occur. So here we have a b value. You would want to say that's a horizontal stretch of 1/3 about the y-axis. So again, I'm very specific with what I need here. I need the word vertical or horizontal. I need to know that it's a stretch. I need to know what factor it's by, and I need to know what line it's against. For 30-1, we will only ever do it against the y-axis or the x-axis, but you still need to tell me that, okay? And the invariant points would be on the line x equals 0 or on the y-axis, however you'd like to state that. Okay, how about y equals 2 f of x? That's an a value, and that's a vertical stretch. So I have a vertical stretch of 2 about the x-axis, and then my invariant points would lie on the line y equals 0, or you could say on the x-axis. Okay. All right, so you are given these 4 graphs. The original graph is the blue graph. Your book is not in color, so it's this guy here, the one that I have as blue, which is the absolute value of x plus 1. Okay, now the green graph, the pink graph, and the red graph are all various transformations on the blue graph. So now we have to try and figure out what transformations have occurred using the little investigation we have below. So the first guy we're going to look at is g of x, where g of x is 3 times f of x. Now, first of all, I would want you comfortable to say, hey, that is a vertical stretch of 3, which means I'm going to take all my y values and I'm going to multiply them by 3. Well, just pick a couple points on the original graph and see where they end up. Okay, so I have the point, take a look here, I have the point 0, 1. If I multiply my y values by 3, that's going to become 0, 3. So that means I'm not looking at graph 3 right now. I'm either looking at graph 1 or graph 2. Okay, but I have to try and figure that out. That's not enough to figure out. Let's pick one more point. So let's go to 1, 2. You see that guy there? The point 1, 2, if I'm multiplying my y values by 3, would become 1, 6. Well, who has the point 1, 6? That's the green graph. Okay, so this is going to be graph number 1. So produce the graph. To produce the graph of y equals g of x, the graph of y equals f of x is stretched vertically by a factor of 3 about the line y equals 0, and it's represented by graph 1. Now, the domain of g of x will be a member of the reals. The range will be greater than 3. Very specific in domain and range as well. You have a choice to write domain and range in set notation or interval notation, but it has to be very specific. If this was being marked on a diploma, just take a look at the range for a second. If you were writing in set builder notation, if you don't have this to start, it would not be considered fully correct. If you don't have this to end, it would not be considered fully correct. If you don't have the squiggly brackets, it would not be considered fully correct. You have to be very, very specific in how you're writing the range. Okay, now it says the equation of g of x in terms of x. Remember, that means I want the actual graphable equation. Well, I know what my original equation was. Here's my original equation. This says take f of x and multiply it by 3. So I'm just going to take f of x, which is the root of x plus, or sorry, the absolute value of x plus 1, and multiply it by 3. So that's going to look like this. I took f of x and I multiplied it by 3. Now I'll clean that up and distribute the 3, and then I'm good to go. Okay, next example, h of x. h of x is going to be f of 1/4 x. Now, I'm hoping, based on the conversations we had on the previous slide, that you would be comfortable to say, hey, that's a b value of 1/4. That's a horizontal stretch of 4. Okay, now let's play around and see if we can figure out which equation it is. And we're going to do the same way. We're just going to start taking points. So on my original graph, I have 0, 1. If I multiply all my x values by 4, my x value there is 0, so that would become 0, 1, which tells me it's probably graph number 3. But let's use another point just to verify. Let's go back to this next friendly point, which is 1, 2. If I took 1, 2 and multiplied my x values by 4, that would be 4, 2. So hopefully that puts me back on the red graph. Let's look. 4, 2. Yes, it puts me back on the red graph. Okay, so I know for sure this is going to be the red graph. So to produce the graph of y equals h of x, the graph of y equals f of x is stretched horizontally by a factor of 4 about the line x equals 0, or about the y-axis. It is represented by graph 3. Again, the domain is going to be real. The range will be greater than 1. And now I want to do the equation of h of x in terms of x. So this now says take whatever equation f of x was and replace x with 1/4 x. So in my equation, x is inside the absolute value graphs. So I'm just going to replace my x with 1/4 x, and that's all I do. That's it. Okay? All right. The next guy is a combination of the first two. So now I have a vertical stretch of 3 and I have a horizontal stretch of 4. Okay? Now, probably you are totally okay to say it's going to be the pink graph, but again, let's just pick a point and I want to show you that it works. Okay? So I'm going to pick the point 1, 2. My x's have to get multiplied by 4. So that'll become 4. My y's have to get multiplied by 2. Sorry, my y's have to get multiplied by 3. So my 2 will become a 6. So that should end up being, let me just write that down for a second. So I want to make sure I'm not confusing you there. I'm looking on the blue graph. The blue graph has the point 1, 2. Okay. I know that my x values have to get multiplied by 4. So my 1 is going to become 4. And my y values have to get multiplied by 3. So my 2 is going to become 6. So I'm hoping that the point 4, 6 lies on that pink graph. So let's take a look. 4, 6. Yes, it does. Okay. So for sure, it is graph number 2. So to produce the graph of y equals p of x, the graph of y equals f of x is stretched vertically by a factor of 3 about the line y equals 0, and then stretched horizontally by a factor of 4 about the line x equals 0, and is represented by graph 2. Now, the domain is real, the range is greater than 3, and now we want to do the equation. Well, there's 2 things happening to the equation. The whole equation has to get multiplied by 3, and my x has to get replaced with a quarter x. Okay, so that would look like this. Now, what I've done there is I've combined those 2 numbers on the absolute value together. You can take out a coefficient from an absolute value as long as it's positive, okay? So that 1/4 that was inside, because there's a 3 on the outside as well, I just took the 1/4 outside and combined it with the 3. 3 times a quarter is 3/4, okay? All right, determine the equation of each transformed function. So the graph of y equals f of x is vertically stretched by a factor of 2 about the line y equals 0, horizontally stretched by a factor of 1/3, reflected in the x-axis and translated 4 units right. Okay, so we're just going to take this piece by piece. If I vertically stretch by a factor of 2, that's an a value. A should be 2. If I horizontally stretch by a factor of 1/3, that's a b value, but remember the b value is the reciprocal of the stretch, so b should be 3. If I'm reflecting in the x-axis, that's a vertical reflection, so now I'm going to put a negative on my a value. And then translated 4 units right, I need to now replace x with x minus 4. A reminder, you already have a number in front of x, so now we introduce that second inner set of brackets so that it's in fully factored form. When you build an equation, it's always in fully factored form. So the correct answer should be y equals -2 f of 3 bracket x minus 4. Okay? All right, good job, guys. Determine the equation now. I've got y equals the absolute value of x. We're going to reflect it in the y-axis. We're going to stretch it vertically by a factor of a half about the x-axis, and then we're going to translate it 3 units to the right. So reflecting it in the y-axis, okay, that's a horizontal reflection, which means I need a negative on my x right now. Stretched vertically by a factor of 1/2, that's an a value of 1/2. And then translated 3 to the right, x is going to get replaced with x minus 3. So again, because there was a negative first, I have to have that inner set of brackets there when I'm building the equation. So I've got 1/2 f of negative bracket x minus 3. Now, I'm going to play with the equation because I had an equation to start with, right? This one actually established what my original equation was. So what I'm going to do is I put a 1/2 in front, okay, and then I replace my x with negative x plus 3. I just distributed that negative, so I didn't have the set of brackets in my graphable equation, but that's where this one comes from, okay? So this guy is in terms of f of x. This is the transformation equation. This guy would say in terms of x, okay? So the green is in terms of f of x, and the blue is in terms of x. You want to be really careful that you understand the phrasing for each one of those. The green one I can't graph, right? Because that f is still there. The blue one, I can actually stick in my graphing calculator right now because that's an actual equation, okay? This green one is more description, okay? All right. So determine the equation of each transformed function. We've got y equals x squared minus 6x plus 10. We're going to vertically reflect about the line y equals 0, and we're going to translate 3 units to the left. So if I vertically reflect, that means I have a negative in the front of f of x. Essentially, my a value would be like -1. And then I translate 3 units to the left, so I replace x with x plus 3. So there is my transformation equation. I'm now going to take this and I'm going to create the actual equation. Okay, so to do that, you need to think about the fact that this is f of x. So if I'm putting a negative in front of f of x, there's going to be a negative in front of that whole thing. But then everywhere where I see x, it's now going to be x plus 3. So I'm going to replace this x here with x plus 3, and I'm going to replace this x here with x plus 3. Okay, so that would look like this. I stuck a negative in front of the whole thing, and then I've got x squared minus 6x plus 10, but I replaced all my x's with x plus 3. Now I want to clean this up. When I square a binomial, remember that you square the first, double the product, and square the last. So this would be x squared. The product is 3x, so double that would be 6x. And then square the last is 9. This -6 gets distributed, so that would be -6x minus 18. I want to clean up in here, and then I also have to distribute the negative. When I clean up, my 6x's are gone here, and then I've got 19 minus 18 essentially, which is the 1. So then I'm ending up with -x squared minus 1 when I distribute that negative into the resulting terms inside the bracket. Okay? Good job, guys. Isn't this fun? Okay. Let's try y equals x cubed plus 2, and it's horizontally reflected about the line x equals 0 and translated 7 units to the right. So if I horizontally reflect, I'm going to replace x with -x. And if I'm going 7 to the right, I replace my x again with x minus 7. So this is what I'm looking at. Now, to actually come up with the equation, there's nothing I'm doing to the whole thing. I'm just replacing x. When I'm dealing with the equation, I don't need this double set of brackets. I only want that double set of brackets when I'm dealing with the transformation equation, or the equation in terms of f of x, because that shows me all the transformations. So now what I'm going to do is I'm going to say, okay, all my x's are going to get replaced with -x plus 7, just to make my life a little easier. And so I have -x plus 7 all cubed plus 2. So -x plus 7 all cubed is essentially -x plus 7 squared, and then you have to multiply it by another -x plus 7. You should probably pause me. If you haven't yet today, this is a good time to pause me. Try and multiply this all out by yourself. Everything's easy when you have me put the answer up, but you try it first. Okay, so you should have ended up, what I've done there is just -x plus 7 times -x plus 7 squared. And then I distributed everything. Okay, so where this line is coming from is -x is getting multiplied by these 3 terms, and 7 is getting multiplied by these 3 terms. And then I just clean it up. My final answer would be y equals -x cubed plus 21x squared minus 147x plus 345. Okay, good job. Now, alas, my time with you is done. But your time is just beginning because you can do homework. So have fun and connect with me if you have any questions. And until next time, we meet again. Take care.